In the ever-evolving landscape of technology, few frontiers are as intriguing and enigmatic as quantum computing. For decades, the concept seemed confined to the realms of theoretical physics and science fiction. Today, however, it stands on the threshold of reality, promising to redefine the very foundations of computation. As researchers and engineers around the world race to unlock its potential, quantum computing is poised to usher in a new era, one that could transform industries, solve previously intractable problems, and challenge our understanding of what is computationally possible. At its core, quantum computing harnesses the strange and counterintuitive principles of quantum mechanics, the branch of physics that governs the behavior of matter and energy at the smallest scales. Unlike classical computers, which process information in binary bits, each representing either a 0 or a 1, quantum computers use quantum bits, or qubits. Qubits can exist in a superposition of states, meaning they can represent both 0 and 1 simultaneously. This property, combined with entanglement, a phenomenon where qubits become interconnected such that the state of one instantly influences the state of another, enables quantum computers to perform certain calculations exponentially faster than their classical counterparts. The implications of this quantum leap in processing power are profound. Problems that would take classical computers millions of years to solve could, in theory, be addressed in mere seconds by a sufficiently advanced quantum computer. Take, for example, the field of cryptography. Modern encryption relies on the difficulty of factoring large numbers, a task that is computationally intensive for classical machines. Quantum algorithms, such as Shor's algorithm, threaten to render current encryption methods obsolete by making such factorizations trivial. This prospect has already spurred a global effort to develop quantum-resistant cryptographic techniques, highlighting just one of the many ways quantum computing could reshape digital security. Beyond cryptography, the promise of quantum computing extends to fields as diverse as pharmaceuticals, materials, science, logistics, and artificial intelligence. In drug discovery, for instance, simulating the interactions of complex molecules is a monumental challenge for classical computers, often requiring approximations that limit accuracy. Quantum computers, by directly modeling quantum systems, could revolutionize this process, enabling researchers to design more effective drugs with unprecedented speed and precision. Similarly, in materials science, quantum simulations could lead to the discovery of new materials with extraordinary properties, from superconductors to ultra-efficient batteries. The potential impact on optimization problems is equally significant. Many real-world challenges, from supply chain management to financial portfolio optimization, involve finding the best solution among a vast number of possibilities. Classical algorithms often struggle with these combinatorial explosions, but quantum algorithms like the Quantum Approximate Optimization Algorithm, QAOA, offer hope for breakthroughs that could streamline operations across entire industries. Yet, for all its promise, quantum computing remains a field marked by formidable obstacles. Building and maintaining stable qubits is an immense technical challenge. Qubits are notoriously fragile, susceptible to decoherence from even the slightest environmental disturbances. Maintaining quantum coherence long enough to perform meaningful computations requires sophisticated error correction techniques and extremely low temperatures, often close to absolute zero. The hardware itself is still in its infancy, with leading prototypes boasting only a few dozen to a few hundred qubits, far from the thousands or millions likely needed for practical, large-scale applications. Moreover, programming quantum computers is a fundamentally different endeavor from classical programming. Quantum algorithms require a deep understanding of quantum mechanics, linear algebra, and probability theory. New programming languages and frameworks are being developed to bridge the gap, but the learning curve remains steep. This challenge underscores the importance of interdisciplinary collaboration, bringing together physicists, computer scientists, engineers, and domain experts to push the boundaries of what quantum computing can achieve. Despite these hurdles, progress is accelerating at a remarkable pace. Tech giants like IBM, Google, and Microsoft, alongside startups and academic institutions, are investing heavily in quantum research and development. Milestones such as Google's demonstration of quantum supremacy, where a quantum processor performed a specific task faster than the world's most powerful supercomputer, have captured global attention, even as debates continue over their practical significance. Meanwhile, governments are recognizing the strategic importance of quantum technologies, launching national initiatives to secure leadership in this emerging field. As quantum computing advances, it also raises important ethical, societal, and economic questions. The disruptive potential of quantum breakthroughs could upend established industries and create new forms of inequality between those who possess quantum capabilities and those who do not. At the same time, the technology offers tools to address some of humanity's most pressing challenges, from climate modeling to disease eradication. Navigating this landscape will require thoughtful policies, robust international cooperation, and a commitment to ensuring that the benefits of quantum innovation are widely shared. Perhaps most importantly, the rise of quantum computing invites us to rethink our relationship with information and computation. For centuries, the limits of classical computation have shaped our approach to problem solving, guiding everything from scientific discovery to technological development. Quantum computing challenges these limits, opening doors to questions we once deemed unanswerable. It encourages us to embrace uncertainty, to explore new paradigms, and to imagine futures that transcend the constraints of classical logic. In conclusion, quantum computing represents not just a technological revolution, but a profound shift in our understanding of what is possible. While significant technical and conceptual challenges remain, the momentum behind quantum research is undeniable. As we stand at the dawn of this new frontier, the journey promises to be as transformative as it is unpredictable. Whether unlocking new scientific mysteries, revolutionizing industries, or reshaping the digital landscape, quantum computing is poised to become one of the defining stories of the 21st century, one whose chapters are only just beginning to be written.